Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 31st lecture on motion planning. All right, so let's get started with a video. Now, this is a video of a serial robot arm that is picking up different objects on a table. The robot has some start position and it moves to a goal position. And the correct goal position changes based on the object I want to pick up. Some of these objects I grasp from the top, others from the side, others from the handle. It really just depends on the object. One thing I think is really interesting in this video is how the robot comes up with this path from the start to the goal. Like, I know my robot shouldn't run into the table or knock over these different objects. I also need to make sure I stay within my robot's workspace so I can reach all these different positions. Well, this question of how we come up with a path from the start to the goal, that's going to be central to today's lecture on motion planning. So first, I want to introduce what is motion planning and give you a sense of some of the challenges associated with motion planning. Next, to better embody these concepts, we're going to practice motion planning with the bug algorithm. All right, so let's get started. Here I have a serial robot arm, and I know I can use control in order to make this robot move to some desired position. So I can take my robot from its initial position to this desired position using control. I can also extend that concept to make my robot follow a trajectory. Now, this trajectory is going to be a sequence of desired positions. So I control my robot to reach its first position, then I control it to reach that second position, and so on. So again, I can make my robot follow this desired trajectory using control. But one of the questions we have is, how do I actually find the right trajectory for my robot to follow? Like in this case, if my robot goes in a straight line from the start to the goal, it's going to run into this box. And so to have the right trajectory, I need to modify this motion so I avoid the box while still going in a smooth trajectory to the goal. So how do I come up with that right trajectory? Well, one way we can do that is by using motion planning. So put simply, motion planning focuses on finding a trajectory from the start to the goal that avoids obstacles. And you can see an example of motion planning over here on the right. I've got my drone at its start position, and I've got some goal I want to reach. And then these objects in gray, those are going to be the obstacles I want to avoid. And so in orange, I come up with this motion plan. Now this would be a desired trajectory that I want to control my robot to follow so it can go from the start to the goal while avoiding these different obstacles. Motion planning isn't all about obstacle avoidance. You can also have secondary objectives. For example, maybe you want to have the shortest distance from the start to the goal, so you want to have an efficient path. Maybe you also care about the energy consumption. So again, you'd want to avoid obstacles, but still find a path that's efficient and your robot doesn't use too much energy as it moves to the goal position. There are some other secondary objectives you might consider, like staying away from humans so you don't run into them, or maybe remaining in some sort of safe space in the environment. All right, a little bit of terminology here. I've mentioned this trajectory before, and I want to define it a bit more specifically here. A trajectory, we're going to call that xi, is a sequence of waypoints. And here are some of these waypoints that you see right here. Each of these waypoints could be a joint position. So theta 1 is a first joint position. Theta 2 is going to be the second joint position I want to reach, and so on. And we can control our robot to follow each of these different waypoints and execute a trajectory. So again, I've got this trajectory xi. It's a sequence of desired joint positions or waypoints, and I control my robot to move along this trajectory by reaching each of these different desired joint positions. Okay, so that's the general setup, but what actually makes this challenging? What are some of the difficulties we face with motion planning? Well, I want to talk you through some of these challenges, and these aren't all of them. These are just some of the challenges that I think are kind of interesting and worth thinking about. And for these challenges to make sense, I want to give you a running example. So let's say that I have a mobile robot, and I want to come up with a motion plan for that mobile robot, and it's in a room of a house. All right, so I want to figure out a path in that room to go maybe from one door to the other door, again, just within this room. So one question you might have is, how much do you know about your environment beforehand? Like, do you know where all the furniture in that room is? Do you know where the doors are? Like, what do you know about that room before you come up with your motion plan? If you know where everything is, you can probably come up with a pretty efficient motion plan right from the very beginning. But if you don't know where things are and you have to detect them on the fly, your motion plan is probably going to change because you'll see something, gather some new information, and then modify your motion plan accordingly. So one question to keep in mind is, how much do I know about my environment? A related question is what I can see with my sensors. So let's stick with our running example. On my mobile robot, maybe I've got a camera and some LiDAR. how far can I see with these sensors and how accurate are these sensors? Like, can I see a table that's several meters away? And with what level of precision can I determine the position of that table? This is going to be pretty important for my motion plan because I want to make sure I can see the things around me so I can avoid running into them. And then the more accurately I can locate these objects, the more efficient I can make my plan. Like if I can tell exactly where the table is, I can move right by it. But if I've got some level of uncertainty, I probably will want to respect that uncertainty when I'm coming up with my more conservative motion plan. All right, so I've got this environment. I'm trying to see things in the environment. What about any sort of moving objects? Like in this room, maybe there's a person who's walking around. Can I detect that person? And if there is a person that's walking around, how quickly can I adjust my plan? Maybe I'm originally planning to go around the table, but then there's a person standing right there. I need to modify my motion plan in order to avoid the human. And the question becomes, do I modify it on the fly or do I have to stop and think for a while in order to come up with a new motion plan? And then finally, does my robot have any dynamic or kinematic constraints that I need to satisfy? Let's stick with our example and imagine that your mobile robot is something like a little car. And we know that if I have a car, I can move forward and backwards, but I can't instantaneously move to the left or the right. I have to turn, and there's some minimum turning radius that I can have. That's a constraint that I would need to consider when I'm coming up with my motion plan. Like my motion plan couldn't immediately take a right turn because that's not feasible for my actual robot. I'd have to think about having a turning radius and making sure that when I use that turning radius, I don't collide with any obstacles. Okay, so again, these are just some of the challenges you might think about when you're trying to come up with a motion plan. To kind of see these challenges in action and better understand what motion planning entails, let's try to make our own first motion planner. And what we're going to start off with is a simple motion planner called the bug algorithm. And again, this is just an introductory planner that I think lets us know about the challenges and kind of how we can develop these planners in practice. So for this bug algorithm, we're going to have a robot, and we're just going to think about this robot moving in a plane. And we're going to simplify everything down so the robot is treated just as a point. So I've got this drone, but I'm just thinking about that as a point in space. The robot does not know anything about the environment beforehand, so it has no clue that there's an obstacle right here. However, the robot can see nearby obstacles. So within this radius I've drawn, the robot can see obstacles, and then outside that radius, it's got no clue. So once it gets close enough, it'll say, all right, there is an obstacle there. The robot also knows its position and the position of the goal, and so it knows what direction it should move in order to move towards the goal. So that's our simplified setting. Again, we're moving in a plane. We've got a point. I can only see objects that are really close to that point, and I want to move towards my goal position. So can you outline an algorithm for finding a path from the start to the goal? And remember that since the robot can't see any obstacles at the beginning of this motion, it's going to need to update its plan as it goes. Like when it sees this obstacle right here, it's probably going to need to adjust its plan and move around that obstacle. Maybe pause the video, think for yourself if you can come up with an algorithm. And perhaps you reach an algorithm like what you see over here. The idea is, while the goal is not reached, I'm just going to move in a straight line towards that goal. So at the very beginning, my drone is going to move in this direction. Once it perceives an obstacle, like once it sees there's an obstacle right here, it's going to start trying to go around that obstacle. Let's say the robot starts moving off to the right. It traces along the obstacle until it realizes, okay, there's no obstacle in front of me. I can start trying to move towards the goal again. And I'll start following a straight line again towards that goal. And I'll just repeat this process until I eventually reach the goal. This would be a very simple bug algorithm. It turns out, though, that this algorithm has some failure cases. I can show you that in the next slide. So here's my robot. And again, I'm going to use that same algorithm. So I start moving from the start to the goal. And then, all right, I've collided with this unknown obstacle. Let me just move around it. So I'll start going around the obstacle. And then sure, I'm going to start moving again in a straight line towards the goal. Oh, okay, there's an obstacle here. Let me go around that. So I'll go around the obstacle. And I've ended back up where I started. And so I could end up in this infinite loop of just continually trying to go around this object, never really getting around it, and kind of ending in this loop. Now, there are ways to break the ties. For example, you could have some randomness where the robot moves either right or left, and you kind of flip a coin to figure that out. But I think there's a little bit of a better way to solve this, and that would be instead of just going directly back towards the goal, I'm going to modify my algorithm so that whenever I see an obstacle, I first circumnavigate the entire obstacle. So I'm going to trace around this entire obstacle. So I'll go all the way around, and I'll move back to my original position. And then I'll trace around the obstacle again to find the point that is closest to the goal. So I move until I get right here. And then I start moving in a straight line towards the goal. Maybe you want to pause the video and think about this algorithm a little bit for yourself. But it turns out that this can be a pretty efficient algorithm for this sort of bug setting. You might be wondering, well, how do you know that it's efficient? Like, what do you mean by even efficient? Like, how do I define a good motion planner? Well, let me explain. There are a couple of things we consider when we're trying to define like how good a motion planner is. And the first thing we think about is something called completeness. So intuitively, if there is a valid path from the start to the goal, I want to make sure that I can find it. And if there is no path from the start to the goal, my motion planner should say so. It should say, hey, this is infeasible. A motion planner is complete if it can do these two things. If it can find a path if one exists, and if it can tell you there is no path if no path exists. So completeness is a pretty desirable characteristic for our motion planners. A second thing to consider is time and scaling. And here when I'm talking about time, I mean the amount of computation time that I need to come up with this motion plan. So how long is it going to take you to come up with the motion plan? And ideally, of course, the shorter the better, so I can modify my plan on the fly. And then how does this approach scale as I reach more complex systems? Like, sure, maybe your motion plan works really well for a drone that's moving in a 2D space, but is it going to work for one of our complex serial robot arms moving in our three-dimensional world and having to avoid objects and et cetera? So how does your motion planner scale up to these more complex and high degree of freedom systems? The last one is these upper and lower bounds. So what's the longest or the worst case trajectory the robot might find? And then what's the shortest or best case trajectory that your robot might find? To better explain these bounds, I want to walk through an example using our bug algorithm. So this is going to refer back to the bug algorithm that we just came up with. I've got my drone, I'm modeling as a point, and I've got my goal position. And I want to think about the best and worst case. So let's consider an arbitrary environment that has n obstacles. And you can put these obstacles wherever you want. It's an arbitrary environment, up to you to decide. What is the shortest possible distance that the robot might have to travel? That's going to be the lower bound. Maybe pause the video, think about it. I mean, to me, it seems like the best case is just there's no obstacles in the way, right? And I can just go directly from where I am right now to the goal. So the shortest distance I might have to travel is d units, assuming that the goal is originally d units from my start position. So that's going to be a lower bound. That's the best possible case I can have. What about the worst case? So to understand this worst case, or the longest trajectory my robot might have to travel, let's say that there's some obstacles that are directly between the start position and the goal. And these obstacles are kind of long and thin, and each of them has a perimeter P. So I've got P1 for the first obstacle, P2 for the second obstacle, and so on. If you remember our algorithm, the idea is my robot circumnavigates the obstacles once, and then it's going to trace back to the closest point. And unwinding those definitions, what's going to happen here is I move towards the goal. All right, there's an obstacle. I'll go around it once. So I'll go around P1 units. And then I have to go around it another half a time to get to the closest point. So I'll have 3/2 times P1. I keep going towards the goal. Okay, I'm going to have to do this whole thing again going 1.5 times around the second obstacle, and so on. And so the worst case is actually going to end up being my original distance from the start to the goal, D, plus 1.5 times the sum of all the obstacle perimeters. And again, these are kind of approximate bounds. So the lowest bound, I think the lower bound of D makes sense, and an upper bound of approximately what you see right here makes sense as well. I'm not asking you to memorize these bounds. I don't think that's particularly important. What's important, though, is kind of the way that we try to analyze these motion planners. So if you come up with your own bug algorithm, you'd probably want to think for yourself, okay, what's the best case? What's the worst case? And how does that compare to some of the other algorithms? And maybe you want to pick one that's got better performance on average would be something to consider. Okay, so we've introduced motion planning, and we've developed and assessed some bug algorithms, which are good introductory motion planners. To reinforce your understanding of these concepts, I encourage you to go through the practice set. You can find it in the description or the pinned comments. The first page has the questions, and the following pages have the solutions. Once you've done that, you can move on to the next lecture. And here we're going to start thinking about state-of-the-art motion planners that we use for serial robot arms. So I look forward to seeing you there.